Hello everyone and welcome to my video tutorial on Introduction to Graph Theory using Python and NetworkX. This is class 6 of the series Shortest Path Problems. My name is Innocent Okoluku. Motivation for the class today is that shortest path problems have practical applications in many areas of science, engineering, and the social sciences. Learning objectives. At the end of the class, participants should be able to define the shortest path, which we will represent with SP, define the shortest distance SD, state the Dijkstra's algorithm, apply the Dijkstra's algorithm to solve a shortest path problem. Content: shortest path, Dijkstra's algorithm, Dijkstra's algorithm example. Now let's consider shortest path. A path or a directed path is such that we have a restriction that every vertex be visited at most once and every edge be traversed at most once while passing through the graph. So if we still recall one of the first diagrams that we used in the class, we have graphs and we have directed graphs, both of which can either be weighted or unweighted. The shortest path problem is the problem of finding the shortest path. So the shortest path is any path of minimum distance from any vertex V to any other vertex U in the graph. We have been considering similar problems in the previous class when we were solving for the minimum spanning tree, that is akin to a shortest path problem. The shortest distance is the weight of the shortest path. Now let's look at Dijkstra's algorithm. Let D equal to VE be a directed network or an undirected network in which the weight of every arc is greater than 0. The algorithm can be used to find the shortest path and the shortest distance from any fixed vertex I in the graph to any other vertex J in the graph, if and only if there is a directed path or a path from I to J. Let Aij be the weight of the arc from I to J. Take note that in some other parts of the note we have used A subscript Ij. There is no need for confusion here. It's because of the way it's written in the book we are using. So they are basically the same thing, whether A bracket Ij or A subscript Ij is the same. So we say Aij is equal to infinity if there is no arc from I to J. Each vertex J is assigned a label that is either permanent or tentative. The permanent label, which we will write as L bracket J, is the shortest distance from I to J. The tentative or temporary label L prime J is an upper bound on the permanent label. At each stage, a set P is the set of vertices with the permanent labels, and the set T is the set of vertices with the temporary labels. Initially, P is the set 1, which contains only one vertex or only one node, and L is equal to 0. L prime J is the weight of every other arc that connects the first vertex to every other vertex in the graph. The procedure terminates when the set P is equal to V, that is, the elements of set P are equivalent to the vertices in the original graph. Step 1. Find the vertex K in T for which L prime is finite and minimum. If there is no K, stop. There is no path from I to any unlabeled vertex. Otherwise, declare K to be permanently labeled and adjoin K to P. Stop if P is equal to V. Otherwise, label the arc IK where I is the labeled vertex that determine the minimum value of L prime J. Step 2. Replace L prime J by the smaller value of L prime J plus AKJ for every vertex J in T. Then go to step 1. Now if we state the Dijkstra's algorithm formally, it's going to look like this. Algorithm Dijkstra. G equal to VE, where V is equal to 1 to N, Lij for all ij in E. Given a connected G equal to VE with vertices 1 to N and edges ij having length L subscript ij greater than 0, the algorithm determines the length of the shortest path from 1 to every other vertex in the graph. Input: the number of vertices N, edges ij, and length L subscript ij. Output: the length J of the shortest path from I to every other vertices of the graph. Initial step: vertex I gets a permanent label and L subscript 1 equal to 0. So in the previous description of the algorithm we just used P, but here we are using PL, that is permanent label, which is a set. The other vertices J equal to 2 to N gets the temporary label. In the previous explanation we just used T instead of TL. There's no difference. L tilde J equal to L1J equal to infinity if there is no edge connecting I and J in G. So we set the permanent label to node 1 and the temporary label will consist of every other node in the graph. So next step is fixing a permanent label. Find K in a temporary label for which LK tilde is minimum and set LK to LK tilde. Take the smallest value K if there are several. Delete K from the temporary label and include it in the permanent label. If temporary label is equal to 5, as there is nothing in the set of temporary labels, then I'll put the permanent labels from L2 to Ln and stop. Otherwise, go to step 3. So in step 3 we start updating temporary labels. For all J in the temporary label, set Lj tilde equal to the minimum of Lj tilde and L subscript K plus L subscript Kj and go back to step 2. End Dijkstra. So the algorithm may not be so easy to understand when you just read it like this. However, when we perform an example, everything will become clearer. We'll do that next. Dijkstra's algorithm example. Example 1. Obtain the shortest distance and the shortest path from vertex 1 to every other vertex in the network shown below. So what we are trying to do in this example is we are going to look for the shortest path from the first vertex to vertex 2. Then we'll look at the shortest path to vertex 3. Then we'll look at the shortest path from 1 to vertex 4, from 1 to vertex 5, from 1 to vertex 6, and from 1 to vertex 7. So the algorithm is going to produce a set of paths from 1 to every other vertices inside the graph. That means there are going to be 2, 3, 4, 5, 6. There are going to be 6 paths that will be created when we solve this problem. So we'll continue. First iteration. Step 1. We create the permanent set, the set of permanent labels. So the first set is equal to vertex, the vertex we are moving from, to every other vertex. Permanent label 1 for the first vertex equal to 0. We set it to 0 according to the algorithm. Every other vertex is going to be a temporary label. So L prime 2 is equal to 4. That is, if we are moving from 1 to 2, the weight is 4. If we are moving from 1 to 3, the weight is 6. We can see it from the graph here. If we are moving from 1 to 4, the weight is 8. So 1 only connects directly to 4, to 3, and to 2. Since there is no link between 1 and 5, 6, 7, it means that the temporary label for L5, L6, and L7 will be infinity according to the algorithm. So only one arc from 1 to 2, and that is 4. So we have already calculated the shortest distance from 1 to 2. So step 2, we set P equal to 1, 2, and the permanent label L2 is equal to 4. This is the first one. From 1 to 2 is equal to 4. Now let's look at the temporary labels. This is the part where we try to fix temporary labels. Originally the temporary label is 6, what we have here, but it is temporary, it's tentative. So we need to be able to fix it, whether we can get something smaller than this 6. So what we do is, since we already got L1 and L2, let's consider L3. From the algorithm, L prime 3 is the minimum between the current L prime 3 and the L2 which we already have, which is this 4, plus the weight of the edge or the arc from 2 to 3. So if we look at 2 to 3, what do we have there? 2 to 3 is 1, and this one is 4. So we are looking at L2 previous tentative label is 6, but this one is 4 plus 1. We are going to pick the minimum between 6 and 5, and that gives us 5, meaning that our previous L3 equal to 6 will now be replaced by the smaller value which we did from the analysis. Let's try to fix L4. The previous L4 was 8. Once we have chosen L2, what we'll be doing on this side is to look for the weight from L2, that's from vertex 2 to every other vertices in the graph. So this is 8 and L2 is 4. What is the weight from 2 to 4? There is no direct connection between 2 and 4, so the weight from 2 to 4 is infinity, and the smaller value between 8 and infinity is equal to 8. That's where we are getting this from. The same thing will go to 5. L5 is infinity because there was no direct connection between 1 and 5. There's no direction between 1 and 6. There's no direction between 1 and 7. So all of them are going to be infinity. In that case, we just take our L to 4 plus check if there is a connection between 2 and 5. 2 and 5 is 7. 4 plus 7 is equal to 11. We do the same thing for this. Infinity plus infinity gives us infinity. L7, infinity plus infinity gives us infinity. So we've done the first analysis, and then we'll go to the next one. So since we have already picked this to be 3, we are going to write out what we have. So we've taken initial step L1 equal to 0 and L2 is equal to 4 and L prime 3 is equal to 5. This is the minimum we got after we updated the tentative label. We are now going to take this minimum label and put it inside the list of permanent labels. We take 3. We've taken 3. So L4 is equal to 8, L5 is equal to 11, 6 and 7 are equal to infinity. So what we are going to do now is, since we have adjoined 2, 3, the arc 2, 3 is labeled. So we've changed this to yellow. We are changing them to yellow one by one. And then the set of permanent vertices has moved from 1 to 2 to 3. And our L3 was updated permanently from 6 to 5. We are now going to deal with L4 by using this L3. So we are going to update the tentative label L4. The initial value from our previous calculation of L4 is 8. So L3 is 5. Let's look at the weight from 3 to 4. The weight from 3 to 4 is 2. So we are dealing with 2 plus 5, and that should give us what? 7. 7 is less than 8, so we are going to take 7 as the update of L4. What about L5? L prime 5 tentative was initially 11. So if we take 5 here and add it to 3 to 5, that gives us 5, which is 10. 10 is smaller, so we take 10. What about 6? The initial value of 6 which we brought from the previous calculation was infinity. So if we take 5 here now and look whether 3 is connected to 6. 3 is indeed connected to 6, that is 4. which gives us 9. We'll take the value 9, so we've updated the value of L6. And if we take L7, 3 does not connect directly to 7, and the previous value was infinity, so infinity plus infinity equal to infinity. So since we are going to 4, the next edge that will be labeled will be from 3 to 4, and the value is 7. So we've labeled it right here now. We are in iteration 3, so we've got L1, L2, L3. So L4 is equal to 7, and we have updated the permanent label with 4. We are now going to continue with 5. So tentative L5 was 10, but now we are going to update it. So what about the tentative value of L5, L prime 5? So initial value was 10, and then we have 7 here. 4 to 5 does not have a direct link, so this is infinity, and the smaller value between both of them is 10, so we take 10. What about L6? Original tentative value of L6 was 9, then we have 7 here, and 4 to 6 is 5. So 7 plus 5 is equal to 12. The smaller value is 9, so we've updated L6. What about L7? So we have infinity here and infinity here because there is no direct link from 4 to 7, which also gives us infinity. So the next label we are going to update is going to be L6. This is the smaller value. So iteration 4, we've now gotten L1, L2, L3, L4, and we are going to adjoin vertex 6 to P, and we'll label the arc 3, 6. So we have 1, 2, 3, 4, 5, 6, and L6 is equal to 9. So we are left with L5 and L7. So we want to update the tentative label of L5. The original value or the previous value was 10. So we are looking at L6, which is 9 here, plus if there is a connection between 6 and 5, that is 1. That gives us 10. 10, 10 is the same. We can pick any one of them is 10. What about L7? Initial value was infinity, and then we are looking at 9 plus 6 to 7, which is 8, and that gives us 17. The minimum between infinity and 17 is 17. So you can guess the next arc we are going to label is going to be from 3 to 5. Iteration 5. So we adjoin 5 to P, to the permanent set of labels, and the arc 3 to 5 is labeled, as you can see in the diagram by the right. So our permanent L5 is equal to 10. We are now left with the last vertex, which is vertex 7. So we are going to fix the tentative L7. Originally the minimum is 17, but we have L5 here as 10, and A 5 to 7 is 6 here, so we have 10 plus 6 equal to 16. The minimum between 17 and 16 is 16, so we choose 16, meaning that the arc 5 to 7 is the one that will be labeled this time around. So in iteration 6, we discover that the arc 5 to 7 is labeled, and then we adjoin 7 to P, and this is what we have. At this stage, P now contains all the vertices 1, 2, 3, 4, 6, 5, 7, which is actually equal to all the vertices in V. We have come to the end of our algorithm. So if we pull out the set of parts that we calculated using the Dijkstra's algorithm, this is what we have. The graph on the right. Now we'll look at the NetworkX example. So I'm going to call it Dijkstra's part 0 to demonstrate Dijkstra's shortest path from node 1 to other nodes in NetworkX. This program is pretty long, not because we are implementing the Dijkstra's algorithm itself. Most of the length of this program is for the purpose of plotting the graph. That's what makes the program long. The Dijkstra's algorithm, as you will see, is already inside NetworkX, but I have not figured out a direct way of just plotting the output in the form of a graph. So I have to write some code to actualize that, as we will see in the program. So as usual, we do the preliminaries and import NetworkX. We import matplotlib. We create the node set for the graph we've already seen, 1 to 7, and then we'll create a digraph. And we are going to add nodes from the node set, and we are going to add edges one by one together with their weights as indicated in the graph. Edge 1, 2, edge 1, 3, edge 1, 4, 2, 3, 2, 5, 3, 4, 3, 5, 3, 6, 4, 6, 5, 7, 6, 5, 6, 7. And we're going to set the positions on the Cartesian coordinates so that the nodes will be exactly where we want them to be. So we have node 1, node 2, 3, 4, 5, 6, 7. We will use subplots because we want to plot the original graph together with the graph we obtained from the Dijkstra's algorithm together in one window. So we'll create the first subplot. If you don't understand what we are doing here, you have to go back and watch the previous videos, and a lot of examples abound. The first subplot is plotting the original graph, and then we'll draw the nodes of the network. We are going to color the nodes yellow, and then we'll draw the labels of the nodes, and we are going to draw the edges and the labels of the edges in a for loop. We create the weights. This is just for the purpose of learning, and then we'll draw the network edges. This example was very well explained in the previous two classes, so I am not going to go over the explanation of them again for the purpose of time. If you really want to understand what is going on here, watch the previous two videos before this. We create the edge labels, and then we draw the labels. Now we obtain and plot the shortest paths between node 1 and other nodes of G. But before we do that, I wrote a function to help split a string of tuples. So after we run the program, I will describe what this function is actually doing. So I'll just go through it now. So we want to get the minimum path from, or the shortest distance from one to other nodes. Now we are going to call the nx.dijkstra's path using node 1 from every other node. So if you want to call the Dijkstra's path, you just say nx.dijkstra and then you state the node that you want and you state the other node. So what I'm using here is a list comprehension to run a loop. Since we are looking for the shortest paths from node 1 to every other node, we put it in a loop. If you don't understand list comprehensions, please watch one of the previous videos so that everything here will become clearer. So what we are saying is, for I in node set, that is for I from 2 to 7, create a list of lists that contains all the vertices, all the shortest paths from I to 2, from I to 3, from I to 4. So what we are going to have as hash is going to be a list that contains lists of vertices from I to every other node, which are the shortest path, the nodes in the shortest path between I and every other vertices in G. So you can print it for the purpose of learning. After we run the program, we actually see what is printed out as hash, so we can analyze it. We create an empty set, another empty set which we are going to use, and later we'll see what it is used for. So in order for us to be able to take these ordinary nodes, in fact, once you have done this, you have solved the Dijkstra's problem. It's as straightforward as this. Whatever I'm doing else in this code is to take those nodes that was returned, put them together, create another graph and replot it. Maybe there is an easy way to do that in Python and NetworkX, but I've not figured it out. This may not be the most elegant way to do it, but what I did here is sure working, as we will see from the graph plot. So we are going to call the NXUtils pairwise to create graphs from all the sets of nodes, all the list of nodes that we generated from here, and we'll do that in a loop. So we say for I in range len h, whatever was returned from Dijkstra, we create a variable, and then we will call this function pairwise to pair the nodes. Every time it pairs, it puts these braces around them which we want to remove. We'll convert it to a list and we'll convert it to a string. If you don't do this, you are going to get some hex data that is not really meaningful when you look at it. So what we are doing here now is the pairing that we created from here, we are adding them to this list h pairing. Next thing we do is we create a flag variable to count the number of occurrences of either the opening bracket or the closing bracket. If the count is greater than 1, we are going to now call the function that split tuples. So if I explain what the function is doing, is this process of pairing is going to create many tuples. If there are many nodes from 1 to some other nodes, like going from 1 to 5, going from 1 to 6 to 7, is going to create several tuples, all of which are going to be bundled together in something like this, which you cannot actually use to create a graph. So what this function split tuples actually does is separate them. If you find more than one of an opening bracket or a closing bracket, we are using an opening bracket here, separate them into different tuples. So we now say split tuples, and then we say from m in the range of whatever is returned from here, this test variable, which is the splitting of all the tuples, we test if m contains either an opening bracket or a closing bracket, use it, because in the process of splitting tuples using the function, in addition to the tuples that are like this, it also returns sometimes another string that is just empty or contain empty string. So we want to strip them out. We want to use only tuples that are returned that contains what actually defines real tuples, either an opening bracket or a closing bracket. That's what this test is doing. We continue. So we now append them. We are breaking them apart. We are now appending them to the new edges we are trying to create. Otherwise, just directly append, because for some links, for instance from 1 to 2, it's just one tuple that will be returned, so we don't need to call the function. This else is when we do not need to call the function, just append what you got directly. So this printing is for the purpose of learning, as we will see when we run the program. This is also for the purpose of learning. What was returned from the pairing, what was returned from the appendages after breaking the pairing apart. Now I observe that the tuples that were returned contains strings from the function. Everything contains strings which we cannot actually use to create a graph. So the next thing we want to do is strip it of all this string notation so that they will become real tuples. So how do we do that? Before we can be able to convert a string to a tuple, first of all, if the string contains this opening and closing brackets, we have to remove them. So we say for each item, because every of this string is included in the list, so we are iterating through the list one by one. That's why we say for I in range len h edge. So we create a variable a1, strip it of the opening bracket, strip this of the closing bracket, so we don't have any brackets around them anymore, because we want to create a fresh tuple from every one of the items in the list. So we now create a new variable and say we use a map. We are mapping from string to tuple, but before then we have to convert to int, and we split using this comma. So we say tuple map int whatever came out from here, and then we split using this comma a2 dot split, and this is going to convert this particular item into a real tuple. So we now change the value of this particular item in the iteration. We replace the original string value to a real tuple value. So once we do that for all of the items in this H edge, we have created a list that contains real tuples, which we can use to plot a new graph. We can see what we did. So now we can create a new diagraph from the parts that were returned from the Dijkstra's algorithm. And we'll begin to plot the second subplot. Every other thing from here remains similar to what we did when we plotted the first graph. We can set a title and say this is the shortest path from one to other nodes of G. In the same way we draw the network nodes, we draw the network node labels. We can just print this for the purpose of learning. Before we can create the labels, we have to extract the equivalent weights from the original G. I think there is a direct method of doing this in NetworkX. I did try it with what I have here and it did not work, so I had to look for another way to do that. So what I did was create a variable, and then we look at the edges in the original graph and try to match it with the edges in the new graph we created. So if there is a match, we are going to take the weight from the original graph and attach it to the edges in the new graph we created. This is where we do the test. If an edge in the original graph is equivalent to an edge in the new graph we created, then we are going to append the particular weight of the original graph to, we assign it to the weight of the new graphs. So it's not like we're actually assigning it to the graph directly, but we are only creating a list of weights out of it for equivalent edges. So once we do that successfully, we've gotten the weights. We can print the weights to see what we really got. Now we'll create a variable that we are going to use to iterate in order to print the edges and labels using the new weights that we just acquired. So we say for edge in m.edges, follow the same procedure we used to create or to draw the edges together with the labels. Every other procedure remains the same, which has been explained in the last lecture or the last two lectures. In order to draw the labels, we are creating these edge labels by using the new weights, which we obtained from this loop. And then we are looping through it using the loop variable h. We can now show the graph. So if you run the program, this is the original graph which we were trying to solve, and this is the graph that we obtained from Dijkstra's algorithm. So now I am going to go to Visual Studio Code and run the program so we can see exactly how it works. So we can see exactly how it works. So this is the program which I just described. I don't have to explain the program again very much here, but I am going to open the console window so that we can see the outputs that are coming out directly and use them to understand the program better when we try to run it. Alright, so this is the output graph from the program. Now we are going to look at the output and see what really comes out, what really came out from this program. So these are the nodes that were returned from the Dijkstra's algorithm. From 1 to 2 was just 1 and 2. From 1 to 3 was 1 to 3. From 1 to 4 was 1 to 3, 4. 1 to 5 was 1 to 3, 5. 1 to 6 was 1 2 3 6. And 1 to 7 was 1 2 3 5 7. You can see that from the graph here. 1 to 7. 1 2 3 5 7. So the way they are like this, if there is a way in NetworkX to convert this directly to the pairing, so we use pairing. However, pairing we use, this is what it returns. So we have this returned as a string, and we have this returned as a string, and we'll have this returned as a string. So you see what it does is it actually takes this and turns it into a tuple. Then it takes this 1 to 2, 2 to 3. So you see 1 to 2, 2 to 3. It's a pairing. And then this one is 1 to 2, 2 to 3, 3 to 4, which is the third one, all the way down to the seventh one. You see everything here is just one string. Unfortunately, we cannot use this directly to create a new graph. So this is where the function split tuples comes in. So what I did was take everything here, put it in a string. After we've put everything here inside, anytime we encounter a closing brace, we put a plus sign in addition, so that later we can use that plus sign as a basis to split the string into a list. So we have individual items which can be iterated through. However, the output from this split tuples is a string of tuples which are not really tuples that we can use to create a graph. So you can see the part of the program where we actually created real tuples from the string. So in that part of the program where I iterated through this list that came from the set, and the first thing we do is strip of the left bracket, strip of the right bracket, and then convert to integer and split using this comma to create a real tuple. So when you created the real tuple, you see that we now have something that can be used to create a graph. And that's when we created the new diagraph M. And these are the nodes of the graph. And these are the edges of the graph, which we use to plot. And using these edges to compare with the edges of the original graph, we extracted the weights using that loop. And it is that weight that we now use to plot the graph. So we have come to the end of the lecture today. Our bibliography still remains the same: the book of Balakrishnan, the book of Edward Platt, the book of Filippo Mensah, numerous YouTube video tutorials. Be sure to check on my video tutorials, and there are also online tutorials. So please like, share, comment, and subscribe for more videos. Thank you, and see you in the next class.